Welcome everyone. So I'm glad you're here taking my ecological modeling course. For this first lecture, I'll be basically introducing you to the concept of modeling. And with that, I'll first ask you, what is your concept of a model? So, what is a model? It's basically a purposeful representation. Most of you have said it's a representation of something, but a key word is purposeful, and we'll go into more detail about why that's important later. So, it's an abstraction of a real-world system, and this representation allows us to deal with the world in a simplified manner. And it's bounded in terms of having a scope. A model is also called problem solving under constraints. So you have a certain amount of information, or maybe a certain amount of time, and in the real world, certain amount of funding in order to come up with a representation of that system and solve a certain issue using that model. So these constraints ask you or make you answer these questions. For example, is this aspect of the system essential for my solution? The problem, that is the question that you're trying to solve, serves as a filter. We're developing models to see if we captured key features of the system and come up with something useful for our question. In engineering terms, a model enables prediction or calculations, or in some other way makes the design process more convenient. So to get you in a mode of problem solving under constraints, here's a very, very simple example. Consider a checkout line or a checkout queue in the supermarket. Now, for you as a customer and as an individual customer, your purpose would be to minimize your own waiting time. However, there's a different perspective if you are the manager of the supermarket. Your purpose, if you're the manager, is to minimize the waiting time for all the customers. So that would mean minimizing the average waiting time for the customers. And the solution would be quite different if you were dealing only with your own personal waiting time. If you're looking into minimizing your own waiting time, then you would probably just try to find that particular line which looks like it has the shortest number of customers and also the least amount of products. And maybe you could be more sophisticated in terms of the conceptual representation in your head of the length of the waiting time, where you think if gender has an effect on the waiting time because of the increase in products bought by certain genders. But however, the manager's solution for this would be one single checkout line for all customers. And this is actually now seen when you go into airport lines and the customs, or when you check in the airport counter, or in banks. They've found that just having one single line for the different windows will actually minimize the waiting time, or the average waiting time, for all the customers. So depending on your constraints, if you're in your perspective, if you're the manager or if you're just an individual, and you're the particular problem, then that differentiates how you will approach in this problem. So now, to get you more fully immersed into the concept of modeling, we'll do a bit of an exercise. So the first part of this exercise is where you individually will take 2 minutes to answer the following questions. So you take a look around you and answer how many ping pong balls will fit into this room. So 2 minutes starts now. Okay, so we'll go through your answers and write down your particular answers. And then we'll go to the second phase of the exercise. You will solve the same problem. However, this time you will work in groups of 3s and take longer, in this case 7 minutes, to answer the same question. So please group yourselves, and the 7 minutes starts now. So obviously, comparing your answers for the second part compared to the first part, there's a difference. There is a difference in the way you approach the problem, because you were a lot more detailed in how you were able to solve the problem the second time around when you were in groups and you had a longer time compared to the first, when your constraints were shorter time, and maybe you can think of it as computing power. So what the real answer is, well, it depends. So now in the second phase, you are considering details of the room that led to factoring in more intricate geometry of the room in relation to the number of ping pong balls, where this wasn't considered during the first phase of the exercise. So that gives you an idea of how you're trying to model something, but you're under specific constraints, and how those constraints can actually mold the representation that you come up with. So, what are the first lessons learned about modeling? It's all in the question. It's pretty key, because that question serves as a filter. In the supermarket checkout line, how to solve that, whether it's one perspective or the other. And then for the ping pong balls, the question could be, why do you need to store the ping pong balls? Is it temporary? Is it long term? Those are some examples. And then a key lesson about modeling is also you need to focus on the relevant factors. There's no way that you can include everything and try to be completely realistic. Otherwise, it'll be as complex and untractable possibly as the real system itself. And then you employ certain ways of abstraction or heuristics, which depend on your conceptual ideas on how you describe the problem. So you use certain theories, underlying assumptions, and this may be specific for certain disciplines, whether it's mathematics or physics or biology, etc., or chemistry. And of course, you create that model depending on your available data and your resources. So those constraints need to be recognized at the start, because those can really shape the assumptions that you have for your model. And ultimately, modelers aren't really a special breed, because day in, day out, we are creating models of certain things as we go on our routine. And for example, in that supermarket line, when we try to find the line that's shortest or fastest, we have certain models or representations of human behavior and numbers of people in the line versus how fast the cashier is, and so on. So we pull that together almost unconsciously, and have models in our head that represent how we think about certain things that we encounter in our lives. So I'll just go through heuristics, because these are examples of the way we model, not just for science, but as I said, even in our daily encounters. So heuristics can be considered as rules of thumbs, or these are the approaches that we empirically know to be useful. So when you're solving problems under constraints, we are maybe subconsciously applying rules of thumbs for modeling the system. And usually, as I mentioned, they become assumptions, and most of the time implicit in the model. So just think of what examples are of heuristics that you have used or are using. Okay, so here are some typical heuristics for problem solving that we commonly employ when we go through the modeling process. Instead of 3D, we represent through 2 dimensions. We use geometric approximations, we average parameters. Just a simple heuristic, we rephrase the problem to be solved to make it more simpler. We draw simple diagrams of the system, or we try to imagine that we are inside the system, and we think of physical laws, or we try to identify essential variables, or simplifying assumptions, or we slice up the problem so that they're in small, more easily handled steps. So here are different types of maps. You can think of maps as models. They represent a certain reality in our world. But as you noticed, this is a map of Sorsogon area, but they represent different information. It's one system, but different topics, and thus different models. On the left, you have your political, municipal boundaries. In the middle, you have your river networks, or your watersheds around Sorsogon Bay. And then on the rightmost, you have the land use representation of the area. So very important is that you don't ever model for a system. You model for a question. The modeling strategy where it's let us model the system first and think about the problems we want to answer later, it's not a good strategy. For example, you're interested in modeling biodiversity. However, you set up the system, but then later on think of the specific specific problem that you want to get a handle on, which is evolutionary change. And in order to tackle that problem, you would need to have particular characteristics and measurable parameters within your model. And if you haven't put those in, then it becomes a lot more tedious to start putting these sorts of traits when you've already created your system. And there's the question of scale of the question, where there are particular factors that are relevant. You have certain structures in the model that are in place already, and you've already planned experiments and have certain available data for the system. But if you didn't phrase the question at the onset when you were creating this model, that you would like to answer, then it becomes a lot more difficult to use the model for that particular purpose. So here's a caveat about modeling, or maybe I shouldn't say caveat, but just a reminder about modeling. All models are wrong, some are useful, according to George Box, who is a statistician. Why is it wrong? Because all models will always be incomplete. As I mentioned earlier, there is no way you can include every single thing in the model. And they're all approximations to what is the truth. And then you have, of course, the parameters or the numbers that you're using for the model that has its own errors. And of course, uncertainties in how you're representing the model or representing the system with the model. Why is it useful? Because it is able to clarify concepts and hypotheses. And models can tease out mechanisms and factors and can really focus research by identifying weaknesses and gaps in the science. So if all models are wrong but some are useful, why go through all this trouble? Why model? And so now we go through some general purposes of models. And there's a broad classification in terms of the purpose of models, according to Holling in 1966. This ranges from what's called tactical to the other side of the gradient, which is strategic. Tactical means models that are quite complex, are realistic and detailed, and the purpose is to really capture the dynamics of the system in detail, usually for increased mechanistic understanding. You have more specific questions, and usually the data for the models are empirically derived. Versus on the other side of the spectrum, you have your strategic models, which are highly simplified, abstract, minimalist. These models are used in order to obtain generalizations about ecological systems. So that's just one way of thinking of the purpose of models, that gradient of tactical and strategic. So in a more application-based approach to thinking of why you should model, one purpose is that it's a scientific tool. Like I said, some models can provide mechanistic understanding of systems dynamics. Think of models as labs or laboratories where you can conduct your virtual experiments. So if you have in situ experiments or in vitro experiments, you also now have the capacity for in silico experiments. Models can reveal system properties and obtain generalizations, and one of their strengths and possibly things to be also wary about is that models can help to potentially forecast what will happen in the future for that system. So models are being widely used in terms of projecting climate change, and this is one of the classic graphs from the Intergovernmental Panel of Climate Change reports, where they try to project temperature change up to 2100 using different scenarios for emissions. And in relation to that, apart from being a scientific tool, that information that you derive from the models can now be used for management. So you have recommendations coming from what you gleaned from the model, and one of the popular terms now for this sort of application of models is decision support systems. You can now examine potential consequences of our actions using these models. And also, one of the strengths of models is that they, at least some of them, can be quite visual. So they can serve as very valuable means of communicating with society, and especially those that are non-scientists. So now we go to approaches to modeling. What are some of the different ways that we can actually do modeling? One is statistical modeling. So they're quite an important class of models because they're widely used, relatively more accessible. These are data-based or descriptive models, statistical models, or correlations or causal models, and they can support, depending on the type of statistics, certain means of extrapolation and prediction. Their disadvantage is that it's still a black box. There's no understanding of the underlying mechanisms and actual causation of the certain processes that's going on in the system. And that's difficult if you're trying to understand what's happening in face of changing processes. So just one simple example for marine fisheries of statistical models are the more complex spatial statistical models, where you have data on the fishery catches, and you layer that as a spatial data, and then you overlay other parameters such as temperature or chlorophyll or water motion, and then see, using a global, using a generalized additive model, a certain type of statistical model, to assess where certain type of fish or whatever your fishery data represents, where they can be most likely found. Now, another approach to modeling is what's called process-based dynamic modeling. So here, you go into the nitty-gritty. You go into the factors, the mechanisms, the processes, the causal relationships, how the system develops through time. So you're able to gain insights into the clockwork, so to speak. And usually there's two typical situations when you're approaching modeling in this way, where there's case A, where you have a lot of data on various details of the system, but you have no idea about their interplay and the long-term effects on the overall system. So you try to put all of those data and synthesize them together into a model. Case B is you see a particular pattern and you want to understand what's happening to the system that's creating that pattern. You have missing information though on the details. What you have is a general pattern. So the modeling can now be a way of testing different mechanisms or factors that actually lead to that pattern. So for example, here there's a temporal pattern from January all the way through different months to December of different phytoplankton species occurring in relation as well to temperature. So there's certain succession of different species through time, and you're not sure why that is, so you can create a model to help explain the emergence of that pattern. So models really become formalized tools for thinking um, in these cases. And now, when you go into modeling, it can be quite an interesting process, because there are many decisions that must be made, whether it's explicit or implicit, and you have to be careful about making implicit decisions that have an impact on the outcome of your model. But it's not really discrete, those decisions that you make. Typically, there's some sort of continuum in terms of trying to figure out which level of description you need to make. So some of the choices that you have to make are these. Some are applicable possibly to you, but maybe others are not. So you can build an abstract model, or you can build a physical model, or some mix in between. You can have static model or a dynamic model, numerical to analytical, deterministic to stochastic, individual to aggregate, continuous to discrete, qualitative to quantitative, causal to correlational, and linear to nonlinear. Here's just some of the things that you might need to think of as you start building your model. So these are actually classifications of different model types. Abstract or physical models. Abstract it's about symbols. It's about logic that constitute the model. You can diagram it. You can have it in your mind. It can be through some sort of programming language or pseudocode or mathematical notation. While physical model is the actual physical replica on a reduced scale of the system. So that's usually seen for engineers. Static or dynamic models. Static models describe relationships that do not change with respect to time, whereas your dynamic model describes time-varying relationships. So, for example, you're trying to project your fish abundance in a certain area through time, as it's affected by different factors, versus a static model which just gives you a distribution of the fish at a certain point of time. Analytical or numerical mathematical models. Analytical models are solved by using deductive reasoning of mathematical theory. So maybe you can, on the most extreme case, you can just use a pen and paper, a few equations, and you solve the model right then and there. However, with a numerical model, there's no formal solution to the mathematical model. So you use computers to try to solve the model. And then you have stochastic or deterministic models. Stochastic means there's a randomness that's built in your model. You use probability distributions, so you can maybe vary, for example, your temperature conditions depending on the average and deviation in a certain season. Versus a deterministic model, you would only use one specific type of input in the model, or maybe one temperature value for that season. Individual or aggregate models. Individual models are where you represent in certain detail your particular individuals or objects and their behavior. Whereas your aggregate models, you represent the objects in the system in a collective way, where you have, for example, only abundance as a representation of your population, compared to individual, where you represent individuals specifically within that population. And then your continuous or discrete models. Continuous models, changes occur continuously, whether this is in time or space, where compared to discrete models where changes occurred at fixed time intervals. And then your models can also be qualitative only, non-numeric models, or they can actually be quantitative. They can be causal or correlational. Causal, that meaning it reflects cause and effect relationships, or correlational models where you put together certain phenomena, however, one is not necessarily the cause of the others. And you have your linear or nonlinear mathematical models, where linear models describe relationships, obviously, in a linear fashion, versus a nonlinear relationship. And all of these can actually go into combinations in how you represent your actual models. So you can have, for example, qualitative qualitative nonlinear models, or qualitative individual based models, or some other combinations of all of these different levels of description, or how you represent entities within your system. It just formalizes how you think of representing individuals, or aggregates of individuals, or relationships within your system. And finally, we've gone through what a model is, why you should model, some of the approaches or things to think about when you're creating your model. Now we go to how do you actually make a model. And I have this diagram here. It looks very neat, but in reality, the process of modeling can be quite circuitous and doesn't really follow these clean paths of this diagram. But generally, at the very start, the most important is that you have a certain problem or certain bounds in terms of what you want to model. So you define the problem, you define your system, and using this problem, then you formulate certain hypotheses and conceptual model of that system using all available information, whether it's general theory, literature, your own data, and you start also figuring out what additional data you need to collect. And then you implement this model in some way. If it's conceptual, then that's kind of where it ends. And then you start figuring out ways to validate your model relative to your conceptual model relative to what you see in the real world. But if you're actually implementing this in other ways, for example, mathematical and or computational, then there are other steps involved. For example, parameterization and calibration, putting in the numbers, plugging in those values that will make your model run, your coefficients, your rates, etc., and then calibrating it so that it actually makes sense in light of the real world. And your sensitivity analysis or other types of performance analysis will let you know if your model is robust enough to changes in values, or how it responds to changing the structure or certain parameters. And that lets you gain more confidence in how your model is performing, and if it looks like it is representing the real world more concretely. And then you go to validation. validation, where you're actually, for example, seeing if your model can capture observations that it wasn't calibrated for, and is it actually, for example, forecasting abundances and distributions in a reasonable manner in terms of what you are seeing in the real world system. And finally, if you have enough confidence in how your model is running, then you can use this model now for specific application in terms of answering your particular problem and concluding and providing recommendations, especially for management, and possibly communicating your results to scientists and non-scientists alike. But I have this asterisk here, double asterisk, saying it's an iterative process. So usually you're implementing it, parameterizing it, but then you revise it again, and then you start thinking about if your conceptual model was actually correct, or were there actually missing components that are key to allowing it to be representing the real world concretely. So it becomes a loop rather than more of a streamlined flow towards application. But this is part of the challenge, and I guess part of the excitement of the process of modeling. So this is ecological modeling. So we go into a little more into what these ecological systems are. And first we define what is ecology. So science, it's the science that's concerned with the spectrum of interrelationships existing among groups of organisms and between the organism and their environment. And to understand ecological complexity, models are, I think, quite important and can play a significant role in this attempt to understand. Because with models, you can use different scales and you can represent all the different variations in the organisms and the environment, and manipulate them in ways that you can actually do in the real world. But always, understanding and modeling hinges on the questions being asked. So though that is still key. You need to have a good question, ecological question, in order to provide a coherent and meaningful, useful model. So there are many applications for models in ecology. At the physiological scale, you have the process of foraging, digestion, growth, translocation, transpiration processes. At the level of the population, you have biological control, species harvesting, spread of invasive species, disease amongst humans. Or at the community level, you can use models to understand stability of the community and diversity, and how different populations coexist together, and their role in species richness. And finally, at the ecosystem level, there's application in terms of nutrient cycling, and, as I've mentioned before, effects of global climate change in different ecosystems. So we'll end this class with an exercise. There will be many exercises in this course because modeling is a process. It's a verb. So you need to be doing it to fully understand that process. And so here we'll already start you with the modeling process, or the modeling framework. The exercise is to develop a conceptual model. So we start with a problem. The problem is that we are concerned about the future of an animal population on a small isolated island that is subject to typhoons. We are particularly concerned because climatologists are projecting an increase in the frequency of occurrence of typhoons over the next few decades. Historically, typhoons have occurred about once every 10 years, although we do not have data indicating the exact years of occurrence. So here I give you some background information as well. We have available data that indicate population size on the island has fluctuated between 70 and 400 individuals over the past several decades. Data also indicate that annual per capita birth rate decreases linearly from a maximum of 0.7 when population size is 50 or lower to a minimum of 0.5 when population size reaches 400. Annual death rate usually is 50%, but increases to 99% during typhoon years. Fortunately, typhoons do not affect annual per capita birth rate, since the young of the year still are buried in the soil as eggs during typhoon season. Currently, as a result of a typhoon last year, only 100 individuals, the majority of whom survived the typhoon as eggs, remain on the island. So, I would like you to create a conceptual model with these following components. What are the state variables? So, what do you need to measure? Is it abundance, biomass, density, concentration? What are the flows or interactions from the animal population flows or that is going on? What are what is the flow of the animal individuals or as an aggregate? This can be mathematical or this can just be a rule-based thing. What are the forcing functions, meaning the key factors that are influencing your state variables, your animal population? And what are the parameters, the certain values that you would need to have some sort of an idea about? Or maybe you have universal constants that you need to consider. For example, your gravitational constant, if that's important. Then you have to also point out what your temporal and spatial scale is. Are you modeling on a day-to-day basis, a yearly basis, decade basis, on a centimeter square area or kilometers, that sort of scale? And also your model currency. Are you talking about nitrogen or carbon or dry weight or number of individuals if needed? So you'll work on this and we'll be presenting your individual conceptual models the next time we meet. If you have any questions, feel free to ask me.